Okay, so to formally carry the proof um, idea that we described earlier in the previous video, um, first we need to facilitate this proof by formally defining the newly introduced finite automaton, the generalized finite automaton that we described earlier. And GNFA, standing for generalized finite non-deterministic finite automaton, is basically similar to the non-deterministic finite automaton, except for its transition function. Its transition function takes as input two states, a pair of states, and then it generates a regular expression over the alphabet sigma, and also it has a start state, like a regular non-deterministic finite automaton, but it only has one accept state. So the set of accept state, we just replace it by just one state. That would be the accept state. So, as such, we define a generalized non-deterministic finite automaton as a 5-tuple Q sigma delta Q start and Q accept, where Q is the finite set of states, sigma is the set of its input alphabet, and its delta is its transition function, which is with the range of the cross product of Q minus Q accept cross Q minus Q start onto the range R, and R is effectively a regular expression. Q sub start is its start state, and Q sub accept is its accept state. Now, why do I actually exclude Q accept and Q start from the input pairs? If you want to think about this, the delta takes a Q sub I and a Q sub J as a pair, and an alphabet, let's call it A. So delta's input is like this, and then it generates a regular expression. So this regular expression, effectively, you can think of it as being the label of the transition arrow. So it basically looks like this. If this is Q sub I and this is Q sub J, then R is the label. Actually, the delta doesn't take the input A, so I stand corrected. You are absolutely right. So delta is in the form of Q sub I, Q sub J, and its output is effectively the label. So notice here, this machine does not read symbols. It basically reads blocks of symbols. And the blocks of symbols are the strings that are created by this regular expression here, and it goes from Q sub I and Q sub J. Now remember, with this special format of the generalized non-deterministic automaton that I said, the accepts and the start state, so Q sub start, always has outgoing transitions, but the accept state also always has incoming transitions. So accept state transitions come into it, but no transition goes out. As such, since this is the start, how would I call it? If you have a pair of states, if this is your source state, so the first element is the source state, and the second element is your destination state, then the Q accept cannot be a source state because there aren't any outgoing transitions out of it. So Q accept is not among the source states. So the source states are all states except Q accept. And the same thing, Q start only has outgoing transition. So Q start only serves as a source state. It does not serve as a destination state, because no transition come into it. So the destination states effectively are all states except Q start. So that's why the delta takes in the form of Q minus Q accept cross Q minus Q start, because these will serve as source states of a transition, and these will serve as destination states of this transition label. Okay, so so this defines my non-deterministic finite automaton in the general form as a 5-tuple. Q is the set of states, sigma is an alphabet, delta is a transition function. It takes a pair of states and it generates a regular expression, and its start and accept states are effectively one state that has all outgoing transitions, and it's your start state, and accept states is one state where your transition accepts, or your machine accepts, and it only has incoming transitions into it. So by this definition, now that we have defined this computation or this automaton, let's see how its computation goes. How does formally one defines the computation of a formal generalized non-deterministic finite automaton? We say that a GNFA accepts a string W over sigma star, or over all the strings that are possibly generated from the alphabet sigma, if there is a sequence of substrings W sub 1, W sub 2, W sub k, from, again, the sequences or the strings over the sigma star, and the sequences of states, Q sub 0, Q sub 1, all the way to Q sub k, such that Q sub 0 is Q start, Q sub k is Q accept, and then for every k, for every I, from 0 to k, if Wi belongs to the language of R sub I, such that the R sub I is the delta of Q sub I minus 1 and Q sub I. In fact, actually, we don't even need a sub I here. So what this means is that if I find a pair of states in terms of my machine, Q sub 0, Q sub 1, Q sub 2, all the way to Q sub k, if this will be the accept state, if the first one will be the start state. So if I start from the start state, but by looking at the transition between each successive sequences of states, this will be my R sub 0, for example, right? Or rather R sub 1. So if R sub 1 takes me from Q sub 0 to Q sub 1, if and only if the W sub 1 will be the language, in the language of, or a member of the language described by R sub 1. So for example, if R sub 1 was A, B star, if the W sub 1 was a member of A, B star, which means that it was a member of, for example, A, or AB, or ABB, or ABBB, and so forth, right? So if W star, if I read one of these members and I transition from Q sub 1 to Q sub 0 to Q sub 1, and you keep doing this computation over and over until you reach the end of your states. So if you ended up in Q sub k, which is the accept state, then you would be then you would accept, your machine would accept the input string W. So just then again, practically very similar to the computation of regular GNFAs, or rather regular NFAs. If you have an input string and you can split that into smaller substrings, and if these three conditions meet, then your GNFA accepts the input strings. If it starts from the start state, if it ends in the accept state, and if it takes the transitions accordingly, by looking at each transition from one state to another state and reading a block of symbols from your input strings. By the time you're done with reading the last block of symbols in the string, if you are in the accept state, then you accept, your machine accepts the string. So now that we have discussed the idea of GNFAs and what they look like and how they compute, we can return to the proof of lemma 1.60, or the proof of the statement that if a language is regular, it is described by a regular expression. So to do that, we pose that we said effectively let M be the DFA for the language. Then we said that we can take this DFA and make it into a GNFA. And now from this GNFA, we basically process recursively by calling a conversion method over this GNFA. So we pass, let's call this G. We pass this G, and this G, the convert operation, will basically call itself. So this convert operation in itself is going to call itself. It's going to reduce G to G prime. So if G had k states, reduce it to a G prime with k minus state, and then call convert over G prime. Now, this is a recursive calculation, of course. And so to avoid an infinite loop, we basically stop this conversion whenever k is equal to 2. So for this operation is going to happen as long as k is greater than 2. The moment you end up with a GNFA with 2 states, you know that you're done, your conversion is done, and so you return the label of the only remaining transition arrow. So formally speaking, your convert operation, your convert procedure will take a GNFA with k states and take k as the number of states in G. Now if k is equal to 2, then it will return the label of R, that is the regular expression on the only transition left. So if you end up with 2 states, so if G was like this, then this will have 2 states in one arrow, and this only arrow will have a regular expression on it. So you will return that regular expression R. If G did not have an arrow on it, if G had more than 2 states, then what we will do is that we will take one of those states as QRIP, with only one caveat, that this QRIP must not be the start state or the accept state. So if k is greater than 2, then there exists a state QRIP from the set of states such that QRIP is not Q start and QRIP is not Q accept. Right? If k is greater than 2, the minimum number k is 3. So since you have a start state and a accept state, if k is greater than 2, there is another state there that's not either the accept state or the start state. So this condition k equal to 2, or rather here basically this means that if k is greater than 2, this satisfies. So this condition satisfies. You can find a QRIP that's not the start state or accept state. So when you found that QRIP, then what you will do is that you will construct a G prime, a new GNFA, that is a 5-tuple Q prime sigma delta prime Q start and Q accept, such that Q prime is Q minus QRIP. So now this Q prime is the set of states minus QRIP. Right? So I took the QRIP out, now I'm left with k minus 1 states. And then for every QI that's not Q accept, or for every QJ that's not Q start, I'm going to calculate the new delta prime of QI QJ with this equation. It would be R4 union with R1, R2 star, R3. Remember the previous conversion idea that we did? We said that if this is QI, this is QJ, and this is QRIP, right? And if this is R4, this is R1, this is R3, and R2 is a self loop over QRIP, then if you do this, then when you convert this into two states like that, with only one transition going from QI to QJ, then this transition will be delta prime QI comma QJ, which from the conversion method that we did earlier, and I made the conversion by taking QRIP apart and out, then you notice that then this label would be going directly from QI to QJ, which is R4, union with going from QI to QJ through QRIP, which would be R1, R2 star, and R3. And we already saw that in the previous video. And this formally defines that if you take QI, any state that is not an accept state, and QJ, any state that's not the start state, you basically compute for all these states the QI and QJ accordingly. And so in this case, R sub I is the transition going from I to J directly. R sub 1, so R sub 1 is directly going from QI to QJ. R sub 2 is the self loop on QRIP. R sub 3 is going from QRIP to QJ, and R sub 4 is well, actually I think I messed up these labelings. I'm gonna go and correct it in the slides, but R sub 1 is going from QI to QRIP. R sub 1 is going from QI to QRIP. So this is from QI to QRIP. R sub 2 is the self loop over QRIP. R sub 3 is going from QRIP to QJ, and R sub 4 is going directly from QI to QJ. And we do this for every state that's not an accept, a pair of states that in which the first one is not a start and the accept state, and the second one is not the start state. And we go over and we perform these modification and alteration of your transition arrows to fix the new GNFA with one less state. Then you call this convert over this new GNFA, and you perform this recursively until you end up with a GNFA that has only two states. And if you have that case, then you basically go and take the remaining regular expression on the remaining transition, and you return that as the regular expression. So let's go ahead and take a look at an example for a non-deterministic for a deterministic finite automaton, and convert that into a GNFA, and eventually come up with its regular expression. So next, I'm going to show you an example. So in this example, I have a two-state DFA, and my two-state DFA, we call this states 1 and 2, and 1 stays in 1 as long as it sees A's. When it sees B, it transitions to state 2, and then it stays in state 2. And state 2 is my accept state for my DFA. So what does this language recognize? If you process it, you would see that it would process a language that is the concatenation of any number of A's followed by a B with the union of A and B repeated in any format, which effectively means that it is a language that starts with 0 or more A's and a B, and then the end would really doesn't matter if it's an A or a B. So as long as you see any number of A's followed by a B, you would recognize that that string. So let's convert this into a DFA, into a regular expression, and see what would be the regular expression describing this language. So this is my DFA, and so step 1 is to convert the DFA into a GNFA. So how does that conversion work? I have a two-state DFA. I add a start state and an accept state. Then I make the start state transition to the start state of my DFA over the epsilon transition, and then I have all of my accept states of my original DFA to transition into this new accept state with epsilon transitions. So this computation is going to be fairly straightforward. So I have my original machine that looks like this, that took a, so this is its start state, 1, 2, and B, A, comma, B. So what I'm going to do is I'm going to add a start state here and call it S and an accept state. So a start state S that transitions with epsilon to my start state, and an accept state that all my accept states transition into it with an epsilon transition. Since I had only one one accept state, I have only one epsilon transition. So if I had another accept state here, then that would also transition with epsilon into it. But in this case, I only have one, so that is it. And so I'm going to call this actually X, just as an accept state, right? I avoid to put A because we might confuse it with one of the letters from the alphabet, because one of the letters from the alphabet is A as well. So that would look like how my machine looks like. Another thing that I need to change also is that, see, this machine has two arrows going from 2 to itself, one for A and one for B. So I'm going to replace this with the union. So the expression for my machine here is going to be AUB, because if you want to think about it, you have the state, and it has one state for A going to itself, and then another for B going to itself. And all you can do is that you can basically make them one, and then make the expression for this to be AUB. So that's how that works. So that is my 4-state GNFA with one accept state, one start state, and the transitions. Now, before actually I go ahead and move forward, let's actually formally define this guy, and let's see how this GNFA works. So how this is defined. So it's going to be a Q, a sigma, a delta, and the S will be the start state, and the X will be its accept state. So I'm going to formally define this now. Okay, so what is Q then? Q is effectively S, 1, 2, and X. What is sigma? Sigma is A and B. What is delta? Delta takes from Q minus Q accept. So it would be Q minus X cross product with Q minus S onto regular expressions. So if you want to see how this would look like, basically you're going to have the input of this thing is going to be ordered pairs, and then the outputs are going to be regular expressions. So the first set, the first orders here are going to be from the sets S, 1, and 2. So these are going to be S, 1, and 2. And then these guys are going to be 1, 2, and X. And then the expressions are going to be S going to 1, which is going to be an epsilon. S going to 2, which is going to be phi, because there's no transitions between S and 2, and then S going to X is going to be also phi. Then 1 going to 1 is A, 1 going to 2 is B, and 1 going to X is also phi. 2 going to 1, you don't have it, so that's a phi. 2 going to 2 is going to be A, U, B, or rather a union B, probably should say it that way, otherwise might get confused with U being a letter from the alphabet. And 2 going to X is going to be an epsilon. So this will look like my transition functions. Notice that if I had a missing arrow from a state to another state, that means that it's a label with phi. So actually, in fact, let me actually write that so that we would see. So effectively, what that means is that this kind of is like a phi is over there, and then also there's a phi over here, and then there's a phi over there. So that's how your machine effectively would look like. Notice that since there aren't any transitions going into S, right? Of course, this arrow going from nowhere means that it's just a start state. But since there are no transitions going into S, S is not going to appear up here. And same thing here, since no transitions come out of X, right? So X is not going to appear here. So these are the ones that transitions go out of, and these are the ones that transitions go into. Okay, so these guys come from there, these guys go from there. Okay, so that's how your transition function looks like if you wanted to kind of know and have an idea as to what's going to happen with them. So next next what we're going to do is that we are going to take one of the states that are not, so this is step 1, converting DFA into the GNFA. So step 1, convert DFA into GNFA. So step 2, perform recursively, perform convert on G. Okay, so what does this do? So in step 2.1, we'll basically take G, okay, and then K is equal to 1, 2, 3, 4. So K is equal to 4, which is 4 greater than 2. So from here, we're going to basically take a non-accept, non-start state, qrep, and then remove it, and then correct all labels, or effectively correct all expressions. Okay, so let's see what's going to happen there. So for now, let's suppose that we're going to take Q2 as the rip. So I'm going to basically now do this. Take Q2, and then so 2 will be my Q rip to rip it apart. And then what I'm going to do is that then I'm going to end up with 3 states. So if I do that, then I'm going to end up with 3 states. Oops, that's a large state. Okay, so these 3 states are going to be S, 1, and X, which is going to be also incidentally my accept state as well. Okay, and now what I'm left is to go for each pair from the states that I have here, to go ahead and compute and calculate and correct their transitions. So remember, Q sub 2 is now gone. So now let's go and look at the pair S and 1. So S and 1. The original transition was epsilon, and I need to correct that. So if you look at S and 1, the original transition going from S to state 1 and it does not in any form or shape go through the state number 2, so that stays. Oops. Okay, so start state. So the transition from S to 1, since it's not impacted by going through state Q rip, it's going to stay there as epsilon. So this transition is going to stay as it is, or it used to be. So nothing really would change on that front. Going from state 1 to 1 also will not be affected by Q rip, because there is no state going from 2 to 1. So state 1 going to 1 itself is going to stay as A. So that's not going to be affected. Now, what will be affected is transitioning from 1 to X. So from 1 to X, there is one transition line, and now this will be effectively going through state 2, which is now Q rip. Now, visually, you can see that to go from 1 to X, you can go from 1 to 2, so that would be a B, and then concatenate that with staying in 2 for any number of operations or any number of repetitions. So this is A union with B star. And then going from 2 to epsilon is effectively concatenating with epsilon, right? Now, the good news is that, so to simplify this operation, you basically take the dots out, so it's going to be B, A, U, B star. And union, epsilon, remember, is the identity operation, or identity for the concatenation. So which means that R, any expression concatenated with epsilon, is going to be the same as concatenating epsilon with any expression, and it's going to be the same expression. So this is what's going to happen. So you're going to end up with B, A, U, B star. That would be the regular expression on the state 1 to X. So we did the conversion, and then we will also still, if you notice here, still K is equal to 3, which is greater than 2. So we are now going to call the convert again on this G prime here. So to do that, I'm going to write this with this black ink. So then I'm going to now rip and non-accept non-start state. This is only state 1. So I'm going to still have S, I'm going to still have X, which is my accept state. So I'm going to still have the state S and the state X, and state S is a start state. And I'm going to rip out this Q1. So 1 now becomes my Q rip. Okay, so when I do this, then there's going to be an arrow between S and X, and let's see what that expression on it will be. So how do I go from S to S? There's nothing, so there's nothing I need to be changing there. From X to X, there's no transition, so there's nothing that needs to be done there. So the only thing that's left is going from S to X. Now you can visually see that going from S to X is an epsilon. So you take an epsilon, and then concatenate that with going from 1 to 1, which would be an A star there. And then that will be concatenated with going from 1 to X, which is B, A, U, B star. Then again, epsilon is the identity for concatenation. And so you can get rid of this. And so then your expression will be A star, B, A, union, B star. And that is how the process converting from a K state to a K minus state works. Now, now we will also still remember, still have to perform the conversion. So we still perform the conversion of G prime. Now, this guy, and when you go there, you see that K is equal to 2, and therefore return R, which is basically label on the only arrow. So now the R regular expression will be then A star B A union B star. Remember here we said this is sigma star, so A star B sigma star. And that is the conversion of my DFA to a regular expression. Okay, we'll do another quick example, and then we'll wrap up the unit on regular expressions. So we have a 3-star DFA. We begin with 3-star DFA, and we would like to see what is the language, the expression that describes its language. So so we've got a 3-state DFA, and this machine has 2 accept states. State 1, state 2, and state 3. And of course, state 2 and 3 are its accept states. And state 1 goes to state 2 with A, and state 2 goes back to 1 with A. State 2 stays in state 2 with B. Then state 1 goes to state 3 with B, and state 3 goes back to state 1 with B, and then state 3 goes to state 2 with A. It's a DFA because every state has exactly 1 and 1 transition for every single symbol, and there is no ambiguity or epsilon transition or multiple choices for this machine. So what I'm going to do is I'm going to have to make another automaton, a GNFA basically, of this machine. So how does that machine look like? So the GNFA then will have a start state and an accept state. So I'm going to draw those with blue. So I'm going to have a start state here that goes with epsilon transitions to the original start state, and I'm going to have an accept state that will go from the accept states. So start state S and an accept state X. And so start state, this new start state for this GNFA now is going to go with an epsilon arrow, and then I'm going to have epsilon arrows going from the original start states into this newly created start state. And of course I'm going to have to remove these start states because these are not going to be start states anymore. I mean accept states. My GNFA will have only 1 start state, and it will also only have 1 accept states. That's how this newly created generalized non-deterministic finite automaton would look like. Okay. Also, with the GNFA, all these labels must be regular expressions. So the good news is that in my machine, I didn't have any repeated arrows or multiple arrows going into a state with different labels to use union. So each of these arrows are a regular expression because each of them are either epsilon or a letter from the alphabet. In fact, this machine also has empty transitions. For example, there is an empty transition here from 1 to 3, so that's a phi there. There's an empty transition from start to accept, so there's a phi there, right? So there are also, this machine also has empty transitions. I'm not just going to show them to clutter my machine, but when you are calculating and coming up with your transitions, sometimes thinking of these empty transitions might actually help with coming up with the with the labels. So that's my created so DFA that is converted into a GNFA. So that's my 5-state GNFA from there. So now from this point on, now I should be going to and converting this machine into from a K state to a K minus state, and then keep doing that until I end up with a one state machine. So from this point on, we're going to recursively call convert G. And as soon as G has 2 states, then we cancel the recursion from there, and we return the expression. So how does that computation work? So for the first step, we're going to make qrip equal 1, right? So we take this 1 here, and this will be now my qrip. This will be qrip. So when I do that, then I will end up with a 4-state machine. S, 2, X, and 3. So my states now are S, 2, 3, and X. And so what I need to do is now to go ahead and fix the arrows from every state that goes to every other state. Okay, so S is a start state. Now, since S is a start state, it doesn't have an incoming transition into itself, but I will have to go and now thinking the state 1 that I took out as qrip. Now I need to go and fix the transition from S to 1, the transition from S to 3, and of course the transition from S to the accept state. But there wasn't any transition from S to the accept state that goes directly through 1, so there's no need for me to go ahead and take care of that. So I would have to do a transition from S to 2, S to 3, 2 to 3, and then 3 to 2 to correct my my machine. So let's see, from S to 2, a transition from S to 2 basically has an epsilon that goes through 1 and goes with A to 2. So it would be epsilon A. And so since epsilon is concatenated with A, since epsilon is in fact the identity element of concatenation, the transition from S to 2 is A. The transition from S to 3 follows an epsilon transition concatenated with a B transition. So this transition here is going to be an epsilon transition concatenated with B transitions. So overall, it's going to be just B. Okay. Then what happens to 2? What happens when going from 2 to 3? There isn't a direct transition from 2 to 3, right? So remember, if I had a state like this and a state like this and a state like this, if there was a direct transition kind of like that, then I would take this. Remember, it was R4, it was R1, it was R3, and it was R2. Then this transition, when you did that, it would be R4 union with going through qrip, which would be R1, R2 star, and R3. So with that, if you look at going from 2 to 3, there isn't a direct transition, but there is a transition that goes from 2 to 1, and then from 1 to 3. So going from 2 to 3 is a transition from 2 to 1 over an A, concatenated with going from 1 to 3 over a B. And remember, this R2 star, since 1 doesn't have any self loop, then this is going to be effectively phi star, right? So so that you can get rid of. Now, how about going from 3 to 2? Going from 3 to 2, then this will be your R4. Okay, so it's going to be so going from 3 to 2, from 3 to 2, you're going to have an A, this transition, union with the transition through the state Q rip, which takes a B and an A, so it's going to be union with BA. Okay, so the transitioning from 3 to 2 will take the direct transition union of the indirect transition that takes the detour from 3 to 1 and then from 1 to 2. Now, there isn't any transition from 3 to 3, so there's nothing that we need to do here, but there is a transition from 2 to 2 itself. So this can actually take this form. Take it either directly from 2 to 2, so you will definitely have a self loop, which is B, but it's also unioned with the way that you can go to 1 and then back to 3, so this is going to be then A. So with one A you can go to 2 to 1, and then with another A go back to 3. Well, actually, you know what? I stand corrected. There is a self loop from 3 to 3, because although there isn't a loop here, so that's going to be a phi, but when you union that with going B to B, then you're going to get a B self loop here as well. So we're going to have to do this. So going from 3 to 3, you're going to have a loop, which would be B, B. Right? Because from 3 you can go to 1 and then back to 3. With B, B, that is your transition. Now, going from 2 to X, there is no route through 1, so you can directly go with an epsilon to X there, and then same thing with 3. So there is only one way to get from 3 to X, and so effectively it's not affected by taking the transition or taking the state 1 out. So next, what we're going to do is we are going to now take the this newly created state, and now we're going to take the state 2. We can take either state 2 or state 3 as Q rip. So for the next call on the of the convert operation, now we make the state 2 to be Q rip, and then we repair our transitions. So now we end up with a 3-state machine, and this 3-state machine will look something like this. Okay, and my states are going to be S, and then 3, and then X, and then the S will be the start state, and then the X will be my accept state. So now for each pair of states, I would have to show and come up with the transitions, which would mean that going from, you take Q sub I and Q sub J as a pair, and then you fix the transition going from Q sub I to Q sub J. So the states that we have that need to be repaired, there's going to be S to X. There's going to be S to 3 that needs to be fixed. There's going to be 3 to X that needs to be fixed. And then there's going to be 3 to 3 that needs to be fixed. These transitions need to be fixed. So from S to X, I would have to see if there is a direct path union with the path that goes through the state 2 to X. So there isn't any direct path from S to X. So the only path goes from S to 2 and then to X. So S to 2 is an A. So this is going to be the equivalent of R sub 1 there. Then 2 to 2 is going to be BUAA, and that's going to be the equivalent of R sub 2 there. So it's going to be union with A, and that's going to be starred. And then from 2 to X, there's epsilon. So you could basically either concatenate that with epsilon, but since epsilon is your union, or is your identity for concatenation, so the transition from S to X is going to be A concatenated with B U A A star. Now this also is the union is a symmetric property. So if you write this down as A and then A union B star, it's still the same. Order in concatenation matters, but in union the order really doesn't matter. So that can also be correct. So the thing that matters is that this operation has a star because it's a self loop through Q rip. Then S going to 3, it actually has a direct path and then a path via Q rip. So the direct path that we have here is B. So you've got B union with the path that you take through 2. So which is going to be through A and then B U A A star and then A B. So it's going to be A B. That's this part here. That's concatenated with B union with A star. That's your R2 here, and then the R sub 1 is A. So I basically ran it backwards because I was going from right to left, but you could also go from left to right. So you go from S to 3. You have effectively S to 3 directly union with S to 2 to 3, which basically this is S to 2. This is 2 to 2 star, and this is 2 to 3, right? So you could do it that way too. Anyway, so it requires some experiment with this, but it's fairly straightforward. It's nothing really too complicated about this operation there. So so going from S to 3, you get B union with A, and then A union with B star, and then AB, and that would be your operation there. And then I would have to go and correct the operation of or the transition from 3 to 3. Remember, 3 to 3 had one transition, and this transition actually also has a direct path and then an indirect path. So the direct path is basically your BB, so that is your direct path, that then unions with the indirect path. So the indirect path goes from 3 to 2. So going from 3 to 2, you get AUBA. So that's going to be A union with BA. And then the star of the loop, which is going to be the star of BUAA star. And then finally going from 2 back to 3, which is going to be AB. So so you would get the operation as being AB union with AA union with B star, AB union with BB. So that will be your operation there for the loop. And finally, I've got to fix the path from 3 to epsilon. 3 to X. So 3 to X also has two paths: a direct route, which is going to be the epsilon, union with the indirect path. And then the indirect path goes from 3 to 2, loop over through, and go to from 2 to 3 to the accept state. So from 3 to 2 is going to be A union with BA, and then B union with AA star, B union with AA, and the whole thing star, and then an epsilon. So it's concatenation with epsilon there. Now, this part is quite important. I have two epsilons, right? I have an epsilon that's union with a bunch of stuff that's concatenated with epsilon. Remember, epsilon is the identity of concatenation. So this you can get rid of. But this you must keep because epsilon is not the identity of union. But here epsilon is the identity of concatenation. Okay, so in essence we could get rid of this epsilon, but we must keep the epsilon union with the rest of this bunch in our operation. Otherwise your expression would be wrong. Okay, now finally what I'm going to do is I'm going to take 3 as the last non-accept non-start state, and from here I'm going to make 3 equal q rep. So when I do that, then I'm going to end up with a start state and an accept state. And so this is the start state, and this is your accept state. With a transition that connects the two. And now I need to fix this transition, and this will be now the R, the regular expression. So the regular expression is the transition that is made of all the transitions from S to X. So going from S to X, I've got a direct path, which is R sub 4 here. Then I've got a path from S to 3, so this will be your R sub 1, the equivalent up here. This will be your R sub 2, and this little thingy here will be your R sub 3, right? So then this R is going to be R sub 4 union with R sub 1, R sub 2 star, R sub 3. So what does that look like? A mess, I tell you. So R sub 4 is effectively A concatenated with A union with B star. Okay, so that is R sub 4. And then that is union with the rest of these. So it's going to be R sub 1. So then R sub 1 itself is A concatenated with B union A star concatenated with AB union with B. That. So that's one thing there. Okay, let's put this in a bracket too. Although these brackets really don't matter, just keeps things a little bit organized. And then R sub 2 star. So R sub 2 star itself is B union with A union with B A concatenated with B union with A star concatenated with AB. So now this will be your R sub 2, and that's star. And then finally this is going to be concatenated with R sub 3. So R sub 3 is epsilon union of A union BA concatenated with B union A star. And then we'll do this, and we'll do that, and we'll do that. Okay, and just clear this union up. And this is your regular expression. So it's going to be A concatenated with A union B star concatenated with BA concatenated with BA union. Wait a minute. Okay, yes. So you got your BB union with BA union with A. And that and there. So that's the star. The B union with A, B union with A star, A B union B. Oh, yeah. Well, that was a mess. I had to myself go through and double check my stars and unions and all that. But yeah, that sounds. This seems to be the irregular expression. Yes. But anyway, I can't emphasize how important it is for you to double check your answers, because just as you can see, a simple symbol swapped or changed could change your expressions. Okay, well then, this is effectively a really good overview of regular expressions, a couple of really important theorems we proved, and finally a couple of good examples about how you convert a regular expression into a DFA, or rather an NFA, and also how you convert a DFA into a regular expression. Remember, the conversion mechanisms we have here are DFAs to regular expressions. So, so this is the end of our Unit 8, regular expressions. We, again, as I said, covered the concepts of regular expressions, their powers, saw a couple of examples of them, and then proved the equivalence of regular expressions and regular languages, or rather finite automata. And as a part of this proof, we actually gained two construction tool sets. A tool set that allows us to construct a regular expression out of a DFA, and another construction tool set that allows us to build a DFA from a regular expression, or rather an NFA from a regular expression. So this topic covers all the way to the concepts of non-regular languages and what is the limitation of regular languages. And we will cover that concept of non-regular languages and the pumping lemma for regular languages in Unit 9. And hopefully you enjoyed this unit of regular expressions, and hopefully it was informative. And I look forward to talking to you in Unit 9 with showing you the pumping lemma and how you can prove some languages to be non-regular.